Okay, today we're going to have a look at complex numbers as vectors. So it's important to note that two-dimensional vectors, which we will cover in extension 1, and complex vectors behave the same with addition and subtraction, but quite differently for multiplication. Now we can also divide with complex numbers as well as raising them to powers or finding their roots, which we can't do with two-dimensional vectors. In vectors, we're only interested in the direction of a two-dimensional vector as a concept, whereas in complex numbers, we're interested in the argument of a complex number, so proofs will involve rotation. We can look at complex numbers as a vector. For example, OU represents the complex number U is A plus IB, and can be viewed as a vector starting at 0, which travels A units to the right and goes up by B units. Its tail is at 0, and its tip is at U. So we know our parallelogram law for adding vectors. It looks a bit like this. So it says that U plus V is the same as this vector here, which is the diagonal of our parallelogram. And subtracting vectors is the same. If we want to figure out what U minus V is, well, we're going negatively along V and over to U. That's U minus V. It's really the same as saying U plus minus V. So recall the tip of the subtraction vector moves away from the vector we are subtracting. Okay. So I've got our polygon law from extension 1. So basically it's saying we've got A plus B plus C, which is just plus D, which is simply going from B to C. And then we've got A plus B plus C plus D. We're just again adding the vectors together. We can see D is the first one on the diagram. So if we add these together, since this is the same as saying D plus A plus B plus C, we're just going along this, and that's going along from there. So remember, a vector is just where we're starting and where we're ending. So the points P and Q are on the complex plane represent the complex numbers Z and W respectively. We're going to mark the point R representing Z plus W and S representing Z minus W. So this is Z here. We've got Z plus, and W there. Z plus W is going to be up here. So if we put our Z also here, so that's W, that's Z, and this is Z plus W. So this is the point R here. Now Z minus W is where we're going negatively along W and then going up to Z. And Z minus W is going to be this complex number here. So Z minus W, we're going Z plus minus W, and it's going to look something like this. So you could, if you wanted to, move the W over to here, and minus W would be that, and you would get that vector there, which is same as this vector here. Now if we wanted to, we can pick up the tip of the vector and move it over to here, and that's our point S, and this is Z minus W. When a complex number is multiplied by another complex number, then starting with the original, we dilate or scale the modulus by the modulus of the second number and rotate the vector clockwise or anti-clockwise, depending on whether the argument is positive or negative, by the argument of the second number. So here we've got U and V, and then U times V, we can see, has been rotated to include the argument of V. So the argument of U times V is U, the argument of U plus the argument of V. And we saw that in an earlier lesson when we learned about modulus argument form, and we looked at the idea that multiplying vectors means we add the arguments. So the work on vectors, complex vectors, is far more likely to involve multiplication than division. However, division is the inverse operation of multiplication, so the effect occurs in the opposite direction. So we rotate by the opposite of the argument in the complex direction, i.e. wrote clockwise instead of anti-clockwise, and we divide the modulus by the modulus of the second number. Okay, dilation. multiplying a complex number by another complex number rotates the original vector by the argument of the second vector. So the argument of z1 times z2 is the argument of z1 plus the argument of z2. So as such, multiplying a complex number by I rotates the vector by the argument of I, which is pi on 2. So multiplying I rotates by 90 degrees, which means that the vector z and iz are at 90 degrees to each other, or at right angles. So we can also look at this idea of multiplying by a complex number in mod arg form. So multiplication by 1 cis theta rotates the vector by theta but does not change its length because there's a 1 here and anything times 1 is itself. And then importantly, multiplication by k cis theta rotates the vector by theta and dilates by the vector by k. So if we have a look at z, we've got z here. 2z, we're not changing its direction. So 2z is just double the modulus of z. So it looks like that. If I could draw a straight line, I'll fix that. So we've got z is there, and then 2z is just double that length. So z, and then this is 2z. A half w, again the half is just decreasing the modulus of w by a half. It doesn't change its argument because we're just multiplying by a constant number. So it's going to look like that. A half w is there. And minus z is just, we're switching the direction of the complex number. So the argument becomes negative. So it just changes the direction of z, but it's still the same length. So it's going to look something like this. A bit like that. That's minus z there. Okay. So looking back at our extension 1 work, it's clear to see that to rotate a complex number without affecting its modulus can only occur if the modulus of the second vector is 1. In other words, we're multiplying it by a unit vector. So we're going to now on the Argand diagram plot the following. Now, in a HSC question, they will place z as the original complex number. I haven't done this, which is my fault in the example, so I'm just going to make up what we want z to be. So z, we might say, what's 2 centimeters long, maybe 3. I'm going to put it up there. That's going to be z. Now iz is the complex number. We're rotating it by I, and the I is a complex number with modulus 1, so it's not changing the modulus at all. So I'm just trying to get this, we want this at a right angle. That looks like that's going to be it. I'm going to do that there. And that's iz, and I'm going to put a right angle in there. 2 cis of pi on 3. We're rotating the vector by pi on 3, or 60 degrees. Now that's less than 90 degrees. So I would say it's going to be approximately here. That's going to be z cis of pi on 3. Again, that doesn't mean the argument is pi on 3. It just means we're adding pi on 3 to the original argument of z, which is theta. Now this next one, we're rotating it not only by 2 pi on 3, which is 120 degrees, but we're also doubling its modulus. So it's going to be potentially over here, adding 120 degrees, but it's also going to be double the length. So we had it as 3 centimeters, so it's going to be 6 centimeters long now. So this is 2z cis of 2 pi on 3. And then finally, cis of minus pi on 2, which is the same as multiplying it by negative I, is going to put a right angle, but we're going in the opposite direction. So that's z multiplied by cis of minus pi on 2. Okay, we'll keep going. We're almost at the end. The conjugate as a vector. The argument of the conjugate is minus theta, since we're simply making the imaginary component negative. So we'll observe that if z is r cos theta plus I sine theta, then z bar is r cos of minus theta plus I sine of minus theta. So we have a look at that. We've got IZ, which is going to be at right angles. So if we draw Z here, IZ is going to be at a right angle, which appears to be there. Again, we don't expect you to use a protractor as long as you are indicating that it's a right angle. And then IZ bar, well, it's just the conjugate of IZ. Something we will learn later is that this is the same as this. So IZ bar is down there, still the same length, and it's just the conjugate, because all we have to do for a conjugate is just reflect it upon the x-axis. Okay, that's everything I'm going to look at in this video. Thanks for watching.